Hello viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're going to talk about SSDs for server. So let's dive right into it. Now, what exactly is the problem? Well, these things basically NVMe M.2 SSD, they become a very big thing, meaning not only they have a superior interface than what server industry uses, which is SATA and SAS, they also have very high throughputs and very low latency, which is very desirable in server industry. So we need to use this. Now you may be like, okay, why can't just use it? Well, that's the problem. They are not designed for hot swappable, meaning server industry values one thing very, one thing above everything else, which is on time, basically uptime. Is it on? Is it working? Yes or no? Now, hard drives, they are mechanical devices. They do fail. Now, the whole server industry knows this for a fact. So they designed hot swappable system, meaning your hard disk goes down, you replace it, you replace a new one, you don't even think about it. Heck, power supplies, they could go bad. You replace it, you don't even think about it. That's the reality of it. Server industry must stay up all the time. Now, thermal output of these puppies started very low, meaning you could have bought like in the early days of NVMe M.2 SSDs, something that is like, naked, quote unquote. Then you start to buy something that are very high performance. Okay, you need some heatsink. Then you would see, okay, now you need a heatsink with good airflow. Now you need heatsink with freaking heat pipes. So you get that point. Like thermal output has reached a point where it's like very hot. So reality is like, and again, these things in your computer, they do not get very hot because again, your computer is not gonna stress them out. But think of it this way: enterprise use, they are always stressing out their equipment 100% of the time, so it will be really freaking hot. So they need much larger thermal envelope. So fundamentally, these things have some limitation. They are not designed for hot swappable large scale. They do not have large enough thermal output to run 24/7 at full stress load. And server industry also desires something what we call density. Now you may be like, why density is such a big deal? Well, unless you are Google or basically Amazon, only few companies have the luxury to actually buy land, build a building, build a server in that. Most companies go to subcontractors, quote unquote, and these people rent out server space, meaning here you can install your server, we'll have a technician team, and you can ask them, like they will do everything. Like the hardware could be everywhere, and this gives them flexibility, like especially for small operators. So they want density. Why? Meaning that rack space is expensive, and on top of that, many server level programs, they have very high end server basically licensing agreement, meaning the more amount of basically processors you are utilizing, the higher their fees would be. They will be like, per processor, like system. So if you are a small time owner, that's good for you. It's like, hey, I only have one processor, cost is let's say $1 million a month, not that bad. You're like, okay, I have 10,000 processor. Yeah, that's expensive. So that's why people want density, meaning they want to reduce the footprint, not only in the space that is consuming, also the hardware that is consuming. So density is something desirable, and whole industry needs to have one standard. That's the whole reason why we have SSD, basically SATA systems, SAS systems working reliably in entirety of our world, simply because it's a common standard. It's like one standard, everybody follows it, every manufacturer makes it, every case manufacturer utilizes it, every Tom, Dick and Harry knows about it. So that's why we need something standard. You cannot have a scenario where Dell is like, I'm gonna make something else, Intel is like, I'm gonna make something else. No, you need one common standard. And SATA and SAS are too slow for flash. They are good, they are very good, they are very reliable, we run on it. But problem is, the moment you start to take about flash systems, again, think of it as the best SAS hard drive, meaning high-end enterprise grade equipment you can buy, will barely go to 400 Mbps, capital B. Now these puppy, they can go up to 4,000. You get that density, really high density. So people want that kind of ludicrously high throughput. SAS and SATA, they are interface limited. So even if you put basically a flash system on there, it's not gonna do much. So this weird name system was created, EDSFF, meaning Enterprise Data Center Small Form Factor. Now be mindful, some companies says that it's not small, it's SSD. I think it's small because they are envisioning more users rather than just SSD. So go with whatever you want, but that's the reality. Enterprise Data Center Small Form Factor. And many companies came together, including, I think apparently Intel is the one that started it out with Intel Blade servers. Basically they had a Blade storage units, and they're like, okay, then they knew for a fact that if Intel is proprietary owner of that, nobody wants to invest in it. That system, quote unquote, it could die out. So they are like, they started to go and have a talk with Samsung, Western Digital, many companies, and all company agreed to that we need a system. We need a new system built for modern day requirement, where you have hot swappable, PCI Express based, standardized, and every Tom, Dick and Harry will know what it means, how to build about it. So Intel, Supermicro, Western Digital, and many more companies came together, and they started to create a standard. That standard is this. Now this standard requires PCI Express. I specified NVMe is the next big thing. SATA and SAS, they are inherently limited protocols. Now PCI Express is a very fat pipe. Now to flow in that pipe, you need a new protocol. You can't use SAS, SATA or SAS. You can use that, like there are adapters for it, but it's like wasting it. It's like, you have a highway that's completely free and you're traveling at like 20 km/h. It's like, no, you need something high throughput. So this NVMe is the protocol that allows you to max it out, meaning if your PCI using 2.0, you will get the 2.0. If you have 3.0, you get 3.0 speed. That NVMe protocol scales very well. So that inherently means even if in tomorrow somebody builds like a PCI 5.0, your speed up will be there. The interface will not be the limitation. Protocol will not be the limitation. Like SATA became a limited system now after SATA 3.0, which was like 6 Gbps, around 600 capital B Mbps. So inherently that will not be the case. PCI Express scales very well. So 3 standards were chosen: 4x, 8x, 16x. Now 4x and 8x are only possible for not possible as in like they are generally used for slim systems. Like I will talk more about that. And then you are a big huge system, they will go to 16x. Generally memory does not need complete 16x unless you are talking about ludicrously high throughput. Like 8x running at PCI 4.0, it's very powerful, as in ludicrously so. So in those sort of scenarios, it's like, yeah, you don't really need like 16x. Now again, this company was thinking way ahead. Maybe today's microcontrollers can't do that. What if tomorrow you build a microcontroller that can handle 10,000 flash chips and like dump data at ludicrously high rate? You have the storage option. So I'm like, it's a very umbrella kind of term. It's not like 3.5 inch or 2.5 inch. It's an umbrella term. EDSFF. So that's the whole point. And I specified NVMe is not basically M.2 was not built for proper hot swapping, meaning the pins in M.2 is linear. Everything makes contact at the same time. Now that's okay if you are rebooting your system. Not acceptable if you are directly gonna pull out. You want to make sure that data pins remain hot, quote unquote, while you are pulling it out, and power connectors are the last thing that gets disconnected for discharge reason. And like there are people who do electrical engineering, they can explain it better, but you can even notice that in your SD cards, there will be some pads that are much bigger and much longer. They're supposed to make contact before anything else does. There is a good reason for that. You always want power rails to be activated before data rails become active. So they redesigned that, like the contacts are designed in such a way. So even though it may look like a normal basically PCI Express system, the contact lengths would be different, and that really makes a difference. Without it trying to do hot swap 1 or 2 times, it may work, or you may fry your whole system. So fundamentally it's a desirable thing. Like they thought of everything, hot swapping. So this is the core standard of it, PCI Express based with slim factor and fat factor, and then they developed from there. Now design wise, I loved one core aspect of it. I never thought of that. It's like hard drive. If you have like a server like this, what is the biggest airflow limitation? Is the goddamn hard drives that are in the front, or like memory system in the front, because they will have what we call backplate. You connect everything to the backplate. Now backplates are quite easy to engineer. Like if you have like let's say 40 hard drives in the front, can you design a backplate for it? Yeah, that's not that difficult. The moment you go to engineer, it's like, hey, can you design a backplate for me that connects 40 SSD with some redundancy? Awesome, no problem. Now say to them, it's like, please have holes in it. Now you were like, how many holes? Not screw holes. I'm not talking about screw holes. I'm talking about airflow holes, because if you do not have that, the fans that are behind this will suffocate. So now you have to have airflow holes, and those are big. Now fundamentally only way to bypass that is like A, you don't. B, you have huge holes. Now your PCB layering is much higher because you do not have enough space for it. So those things become expensive, and they still choke the airflow. They call it in the industry, it's called air dam effect. So there is a dam behind the memory unit. Now this puppy, they knew about this. This is a big issue. So what they came up with is 90-degree connectors, meaning you will have them basically backplate, and connector would be like this. Right now the old system is like backplate your drives, but right now it will be like this. Backplate, completely big thing, so you can design as complex PCB as you need, as many big microprocessor you want. Oh, this microprocessor is blocking air hole. No, don't worry about it. Go you'll on it. And the connectors are 90 degrees. Benefit of this, the connectors are designed in such a way that they are a bit slimmer than the hard drive that is coming in. So space between each hard drive is free. There is a complete airflow, so air can directly pass through. Basically how servers always have RAM stick aligned with the airflow, it's like that. So that's amazing. Like without it, simply it will cook itself, or the fans will keep burning out very quickly, because the fans that go into server system, they can almost pull vacuum. If you have an air block system, they can almost pull vacuum, and they consume lot of power, as in like hundreds watt. 200 watt, 300 watt, and they're expensive also. So on top of that, if you can create a system that inherently allows proper airflow, they have noticed like 20 to 30% energy reduction. It's like, how the heck that much energy? Yeah, fans are relaxed and everything is running, you know, much more calmly, quietly. So everything is happy. So airflow, awesome design. Then they have two core categories I specified. They have 4x, 8x, and 16x. Now 16x need what we call E3. It's like, think of them as 2.5 inch, normal 2.5 inch system, that is E3, and they have E1. I have no idea what happened to E2. Now E1, if you want to visualize how thick that is, like as in like how high it is, it's U1 standard, meaning if you take a server, the smallest rack you can build in a server is what we call 1U unit. Now this is designed for 1U unit. Now Intel, when they were initially working on that, on the system, they had a goal in mind. The goal was that they can sell to other companies one server that is 1U in the size, and they will have nameplate capacity of 1 petabyte. Let that sink in. 1 petabyte of server grade equipment in 1U system. So that's why everything was designed from day one to accommodate that. That was their end game. It's like at least achieve by the end of 2019 1 petabyte in 1U chassis. So they have basically E1 standard, that is designed for U1 basically one standard unit. It has two categories. One is short, one is long. Now short ones are basically for everyday use, as in everyday normal server use. But if you have a server that is specifically built for data hoarding, basically Netflix servers for example, you're gonna use long ones. Long ones will give you larger capacity. That's how Intel achieved 1 petabyte in one location. Now if you do not need that, if you all you need is like, you know, hey, I instead of needing 1 petabyte, I only need, let's say, 200 terabytes, use the short one. Simple. So these are the two basically long and short protocols. And then you have E3. Now E3 are generally not supposed to be used most of the time, simply because they are way too powerful. Because you're talking about, if storage you are talking about, running at PCI 4.0, running at 4x is more than enough for almost everything. This puppy is run at 16x. So they have basically they are overkill, but they have built it because like right now the memory controllers can't utilize that. What if tomorrow's memory controller can utilize it? What if tomorrow you have a you know, quad layer flash systems that are very powerful, very robust and reliable, and they can actually handle the throughput? Then you will utilize that. So they built it everything like, you know, thoroughly. So this E3 will have the benefit that everybody who's used to U2 basically U2 system, which was a, like, you know, carry over system from SAS system, it was not very successful. That's why people are going into this system that was supposed to allow you know, SSD hot swapping and all that. Just it was not very successful. It was not built very properly. So if companies want to jump from that manufacturing system to this, they will go to E3, because going to E1 they need to redesign a lot. Going to E3 they just have to redesign the connectors, and most of the time connectors are also the same. They just have to realign the pins. So E3 is basically carryover, but it does have unique ability that this puppy can only go to 8x, this can go to 16x. So if you need a scenario where you actually need to utilize 16x, you have the interface. So they built a umbrella system with everything in mind. So if you want, like, you know, normal basic capacity, go with E1S, basically short. If you want ludicrously high data density, meaning you want to have entire Netflix backed up in, like, you know, one server rack, go with E1L, long system, and you can have like ludicrously high data density. But if you need something, let's say hard drive that is so fast that is inherently acting like a RAM, then go with E3. It also has the short and long. It's like, why? But it has it. I can't do anything about that. Now that's the two categories that you can easily understand. That means there are four systems. You have E1, long or short. You have E2, that is E3, that is long and short. And then there is like, somebody came up with, what if we have thickness variations in there? I have no idea who came up with that. It's like, generally I don't know. It's like it has thickness based on its thermal capacity, because you have to understand that your thermal system you are seeing in your SSDs that is running your gaming end system, it's not designed to work 24/7. It's like more like, you know, you load a game, it's like dump a load, then it calms down. Enterprise does not work like enterprise is like 24/7 full steam ahead. So in those sort of scenario, they know for a fact that people will have different thermal requirements. So the lowest thermal envelope you can build is 12 watts. So if you are talking about like just image storage, go with 12 watts. You're talking about something that is, you know, a bit high end. Generally, people are now standardizing to 20 watts. So even the you know, basic unit should be able to dissipate 20 watt of heat, meaning the flash chip that you are putting should output 20 watt at its max load. And then the server units can easily handle it. That has the thermal envelope. Now you may be like, what if I need a bit more? You can extend the system so airflow rates goes down, but you will have still 20-watt thermal envelope. But you're like, no, I need more thermal envelope. You can go to 25, which is 25 millimeter. Now it has like a freaking heat sink. Now inherently this is designed for something that is like a bit more experimental. Let's say PCI 5.0 comes in, the first generation will be much hotter because it takes like new technology, very high thermal output, then it gets optimized. So during that time you can utilize like 25 form factor. So not basically you have to know all three dimensions. Dimension number 1, E1 or E3. Dimension number 2, short or long, applies on both of them. Then dimension number 3 is like how what is the thermal envelope, meaning thermal envelope could be 25 watt, 40 watt, and that same goes with E3 systems. So that is a bit weird. And E3 can go upwards of 70 watt. Now 70 watt is a lot. That's like almost low end graphics card kind of thermal output, so you be mindful of that. Yeah, I have no idea who came up with this. Like, I get it, like E1, E3, I get it. If I don't call you E3, I have no idea, but like, okay, long and short, still get it. But the moment they started to create thermal envelopes in that does not make sense to me. But again, I hope they have some use of it. But every server that I'm seeing that is actually available for sale, they are for 20 watt units. So that is a bit weird. It's like apparently nobody built 25 watt units. Now, I specified that this is a PCI Express system and they are not focusing on SSD only, because if you enterprise is always one generation ahead. So right now you can buy enterprise that has DDR5. So DDR5 running at 4800 megahertz will give you a 38 Gbps. That's fast. Now PCI 5.0, which already exists in basically enterprise environment, goes to 16x. If you use that basically E3 system, goes to 36 Gbps. Now you may be like, okay, what does that mean? That's still a bit less. Now, but here's the interesting part. That inherently translates to you do not need RAM. You do not need RAM because PCI Express directly talks to the basically processor, and if it has that kind of throughput, you will literally have to dump the entire processing data directly to the system. Because right now what RAM does is like you take the data from tier 1, tier 1, it would be the wrong way to say it, let's say tier hard drives. You take the tier hard drives, dump it into RAM, then RAM sends it to the processor for crunching. But what if you do not have to do that? What if you can directly connect the processor to memory, and memory is fast enough where it can dump the data directly? And PCI Express inherently does not have the latency and side effect which was associated with SAS and SATA. So you can utilize that. That's the whole point of NVMe. It's direct connection. So that's why in future you could literally have an inversion of memories, RAM requirement on server. RAM requirement could go from, like right now we are like 1 terabyte RAM, 2 terabyte, 4 terabyte, and then it will go, just put enough that operating system can run on it. And then the whole data crunching, that was like is fast enough, where it's like you just don't need, basically you do not need to dump from slow bucket to fast small bucket, and then fast small bucket feeds the processor. You can directly direct feed it. So that is a very critical aspect, and that's why they are no longer just focusing on one thing, like 1 petabyte in one U chassis. They are also focusing on other things, and that's why that thermal headroom was very critical. That thermal headroom with PCI Express allows them to do lot more things. Data storage is like bare minimum capacity. After that you can go YOLO. For example, memory accelerators. Now these puppies are used for if you are trying to do what we call compression, encryption, decryption, things of that nature. Memory accelerator, you can just have that. It will be like a compute card. You can have front side networking, meaning because these things are just a basically hot swappable PCI Express port, you can just have a fiber optic there. And because this was designed with three thermal envelope in mind, you can have 25 watt unit, because optical fiber that is running at around 100 Gbps, they do have thermal output, like they get hot. So you can use that, still use the same back plane, but utilize the higher thermal output. And many more uses. Like there are some people who are talking about, like if you have noticed recently, Intel released a pen drive that was for boosting neural network processing. Just use that. It's like, of course it will be better, much faster and much more efficient than using USB protocol. So you can use that, and it has the thermal room, it has the electric basically protocol headroom, everything is there. So this is multi-use system. Do not think in like, okay, SSD done, go home. SSD is step 1. After that there will be many more things. So what we can expect in the future? Well, reality is server industry moves very slowly. They take their time, they are very cautious, very thorough and all that, but they are now finally reaching a point where SATA and SAS will be obsolete. And then next technology will come in, which is CXL. Now CXL is basically Computer Express Link, which is a bigger brother of PCI Express. Now PCI Express is like a legacy standard, PCI 1, because that's why all the equipments are backwards and forward compatible. But if you look into enterprise grade brochures, you will notice CXL memory module. What the hell that means? That simply means basically PCI 5.0 speeds with a bit more modification. It's like it's a open standard, so every company that is working on this, they can directly contribute, and like, you know, it's like almost like Linux. So this puppy is much faster, much more robust, quote unquote. So that's why like this puppy can almost reach a point where RAM would be like just bare minimum. You're like, instead of having terabytes of RAM, you'll just have a head to just have a compute module. Not for this, because these can only go to 8x, but that thicker unit, E3 units, they can go with like, you know, just replace the RAM, like, you know, instead of 2 terabytes of RAM, just buy basic amount of RAM. And I do find it a bit complicated. It has too many standards, because I get it, like 4 standards I understood is like the moment they started to introduce a third vector, basically each could have different thermal envelopes. That was a bit weird, but let's see what happens, what interesting uses that comes into the market, because I really like that small thing. That backplane is a very big air block. The fact that they thought about it is like, it would be easier to design a PCB that is like this rather than a PCB that is like this, and not only has connector and also has to route PCB's microprocessor, and doing that with NVMe level speeds with running PCI 4.0, that would be very complicated. So I like that idea, and the fact that it will help your fans remain cool, awesome. So let's see what future holds. So this was my presentation on SSD on servers. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.